Everyone. So I could not figure out how to show myself and the screen at the same time on my current laptop setup. So I will just be sharing with you what's in front of me on my computer screen. What I would really like for all of you to do is to go into Schoology and find what's labeled as exercise 16.1. There will be a PDF file that is these practice problems. These are the practice problems I'm going to have you do today. It'll take you up to 2 hours to work through everything at most today, and it'll be even shorter if you're doing decently with K and Q, our equilibrium and constant and quotient, right? So if you're comfortable finding K, then today it shouldn't actually be that much more difficult. It's just a little bit different. Okay, so I'm going to model a few of the problems and then you're going to go ahead and practice on your own. I will also have an answer key in the same Schoology link so that you can check your work as you go. So the first one I'm going to model is actually Cu2S. I'm going to be modeling this problem. It says write balanced equations for the dissolution reactions. Dissolution just means when it dissolves, to break apart, and the corresponding expressions for the solubility products. So that's another fancy way of saying Ksp, the expression for solubility products. In addition to this, you should watch the videos I've assigned on AP Classroom. They'll give more clarity than I do and more details than I do here. So that's another resource you can use. They'll also be linked in today's materials. Okay, great. So again, Cu2S. I want to figure out what this breaks apart into. So I'm going to show you how I imagine it. Okay, so here we can see that we have C2S present, and I've drawn it as a molecule, 2 Cus and 1 S. When it hits water, it's going to dissociate. It's going to break apart into its parts. We can see here it's going to make 2 coppers and 1 sulfur. Because of where sulfur is on the periodic table, group 6A, I know it's going to have a -2 charge, and copper is going to have a +1 charge, so it can be balanced. 2 +1 charges for a +2, and a -2, it'll be balanced. Now, this is me just showing you that this would break into its individual pieces of 2 copper ions and a sulfur anion. That's useful information because that'll allow me to create my balanced equation. Copper sulfide can dissociate to form copper and sulfur. Now there's this double-sided arrow because when you dissolve things, if you add enough salt, which is just an ionic compound, metal, non-metal, when you add enough, it literally will become saturated and it can't hold any more of the ions, and so it'll stay as a solid. What you don't actually see happening with your eyes is some of it dissolves and then some of it reforms into that solid. It's constantly happening. That's what happens when you have a saturated solution, when there's so much salt that it can no longer dissolve. It's actually dissolving and turning into a solid, precipitating at the same time. Great. So the problem asks us to write this equation, my balanced equation, and to find K, it's the same as we've done before. K is now Ksp. Sp is for solubility product. Solubility means dissolved products. Here are my dissolved products, aqueous. It's equal to products over reactants. Now, our products are Cu plus 1 and S -2. This coefficient of 2 becomes a squared on copper. And if we were doing an ice chart, that coefficient of 2 would mean that the change would be twice as much for copper as it is for sulfur. But in our K or Q equation, it's the exponent. Here it's 2, here would be 1. Now, it's products divided by reactants, but my reactant is a solid. And if you remember from what we learned before break, solids are not included in our K or Q equation, nor are liquid, only gas and aqueous. So because of that, this is my final Ksp equation. Great. So the only thing I do foresee being a little bit more difficult is an example where maybe you're not sure how to break it apart. This is one of the problems also on the PDF file, calcium phosphate hydroxide. In parentheses, automatically, that should ring a bell that these are polyatomic ions. So these are ions that are made out of multiple atoms. There's some of the ones that we had to memorize before. And again, we'll still need some familiarity with. Oops. So when I do this, I know I'm going to break this up into 5 calcium ions. Calcium is a positive 2 charge. And then I'm going to break it up into 1 hydroxide ion, which is a -1 charge. And then I'm going to break it up into 3 PO4 anions, which all have a -3 charge. I know these charges based on memorizing my polyatomics. PO4, 3 negative, hydroxide is always -1, and calcium is a positive 2 because it's in the second group of the periodic table, group 2A. So I can now write my Ksp equation based on this. It'd be calcium to the 5th power times phosphate to the 3rd power times hydroxide to the 1st power. Great. So at this point, you can pause and then try the first few problems, and then move on once you've practiced those and checked your answers. Cool. If you're coming back after finishing these problems or just wanting to continue, then something we're going to look at is, well, how useful is ice in this? And we're going to do that by looking at number 10. So I'm going to pull up number 10 right here, scroll down, and I can see that's asking me for the molar solubility of Bi3, which is bismuth iodide. So it tells me that it has a solubility of 1.3 times 10 to the -5 moles per liter, and it wants me to find the Ksp. Great, so I'm going to go back to my document camera, and I've written down this information. I'm not going to draw any more visuals because you should have enough practice by now, but if I start with Bi3 solid, when it breaks apart, it'll form Bi positive 3 aqueous, and it'll form 3 iodine ions that are -1 aqueous. From here, I can write my Ksp equation, or I can write ice first. So ice, initially there's none of this or this. We put the salt into the water, it starts breaking apart. The change is, well, I know Bi3 has a solubility of this. So this is breaking down at that rate, that many moles for every liter. So I know that for every one of these that gets broken down, I make one of these. So if I say plus x, this is the same thing as my x, because this is a 1-to-1 ratio. I'm just going to write that the change is 1.32 times 10 to the -5th molarity, and then the change here would be 3 times this, 3 times as much. So when I break down one of these, I make 3 times as many iodine, so my change is 3 times as much for iodine, 1.32 times 10 to the -5th. And so my equilibrium values, this one stays the same, and this one would be multiplied by 3, which would make it 3.96 times 10 to the -5th molarity. Now, the question was asking you, what is the Ksp? Ksp, like any K, is products of reactants, which is our Bi products times 3i -1. And that 3 is actually in the wrong place. 3i -1, it's I -1 iodine, but because it has a coefficient of 3, my exponent becomes 3. Remember, the coefficient only matters for your change and for your exponent in the K equation or Q equation. So from here, I can now substitute my values. I can substitute in 1.32 times 10 to the negative fifth times 3.96 times 10 to the negative fifth to the third power. And when I plug this in, I'll get my final answer. You should all be practicing your calculations. So if I go check the answer key for number 10, you can see here that they did the same math as me. You should get 8.20 times 10 to the negative 9. 8.20 times 10 to the negative 19, oops, is my KSP. That is my KSP right there. Great. So this ICE table helped me organize my thoughts, and that's why it's super useful for us to keep using that ICE table. We should also be mindful of things like number 11. So if I check out the wording on number 11, it wants us to find KSP again, but it gives us milligrams per liter. Now, milligrams per liter is not the same thing as moles for every liter. So I know I have 65.9 milligrams for every liter of iron to oxalate. Which I'm just writing down on a piece of paper. And what I want to make note of is when I have 65.9 milligrams per liter, I don't want milligrams for every liter. I want moles for every liter. And you can notice that liter is going to stay the same. I just want to change milligrams into moles. That's when we use stoichiometry. So if I start with 65.9 milligrams, and I'll keep the liters just to show you for every liter. I don't want milligrams, so I need to multiply by a conversion factor. Milligrams will cancel milligrams. Well, I don't know how many moles are in milligrams. I need to go to grams first because the periodic table uses grams. I know 1 gram is the same as 1,000 milligrams. So I now effectively have grams. Using the periodic table, I know that a set amount of grams is equal to 1 mole. Now, the set amount of grams is the molar mass of iron oxalate. So I would have to find the molar mass of that. Just to speed things up a bit, I can see here that iron oxalate, the formula is FeC2O4. If I didn't know how to do that on my own, then I could also just Google it or use inferred guesses or know my polyatomics. Oxalate is one you have to memorize, which is C2O4. It has a -2 charge. And then it says iron 2, which means it's a +2. So +2, -2, they combine in a 1-to-1 ratio, which is how they got that chemical formula of FeC2O4. Okay, another one that I think you should be shown before you practice these on your own is number 13. In number 13, the directions are at the very top. You want to find the moles per liter of that substance. Don't worry so much about the grams per liter. Moles per liter is enough. Your stoichiometry will get better as it goes. So focus on moles per liter, molarity. But for number 13, it wants us to find the molarity of this compound, knowing our KSP. So for this one, I know that we have a KSP 6.1, which I'm going to write down. KSP is equal to 6.1 times 10 to the -5th. And we're looking at CaSO4, calcium sulfate. So CaSO4 is our solid, and it would break down into 2 ions. It would break down into calcium +2 and sulfate SO4. Now I can start to create an ice chart around this. If you're wondering why I'm ignoring this, it's because this is a solid and it's going to be saturated anyway for this to exist in the first place, so it doesn't really change. Here, though, I'm imagining this is at the very beginning as this gets dissolved. The initial amounts would be 0. I would make this product and this one too. It has a 1:1 ratio. So it's a plus x and a plus x. There's no coefficients to worry about. So our equilibrium would be x and x. Now, when I look at this, I know that my Ksp is 6.1 times 10 to the negative fifth. So Ksp is equal to products over reactants, which in this case would be x times x. There's no coefficient, so it would be, there would be no exponent. So this is the same thing as saying x squared, which is equal to 6.1 times 10 to the negative fifth. To get rid of that squared, we just have to take the square root of both sides. And when we take the square root of both sides, we can go ahead and check our answer for number 13. And we'll see that they get 7.8 times 10 to the negative third. 7.8 x is equal to 7.8 times 10 to the negative third molarity. Because those represent concentrations. So in your calculator, you should be able to get 7.8 times 10 to the negative third molarity. That is the solubility of both these ions in terms of molarity, moles per liter. I know it asks you for grams for every liter, but don't worry about the grams for every liter part. Okay, one last ice chart that I want us to look at before you just continue practicing on your own is from problem 20b, because it does incorporate a concept where you kind of just ignore something. If you've been noticing, these E values, equilibrium values, are really small. Like, I barely make any of this, right? This written as a number is the same as 0.0078 molarity. A very, very small amount of ions is formed, like super, super low. And you can actually use that to your advantage to speed up some problems by making an assumption. This is very common on the AP exam where you'll be given a multiple, not a multiple choice, but a free response question. And you'll have to make an assumption to speed up your math. As long as you claim your assumption, you are rewarded with the points usually. And this assumption is pretty safe to be used. It's even covered in the videos that I've assigned for today also on AP Classroom. So the one I wanted to look at was 20b. It's different than 20a, and I'll explain why in a second. It says the Ksp for silver sulfate, this compound, is 1.2 times 10 to the negative 5. Calculate the solubility in each of the following. So in water, it just breaks apart. But in AgNO3, you'll notice that we already have Ag present, and we're making Ag. So we already have some Ag, but we want to make more Ag, and this is where Le Chatelier kind of comes into play, where it'll affect your solubility because I already have some of the product. My product side is already heavier than if it was just being dissolved on its own in water, which means it'll want to make more reactants, which means NO3 is going to be consumed and Ag is going to be consumed just because of how Le Chatelier works. I already have some product, and I'm going to consume some of my Ag and SO4, my bad, to go back into my reactants. So that does affect your Ksp because your equilibrium was shifted with the presence of this. Now, how does that look like using ice? Let's set it up. I'm going to quickly, on my paper, copy down Ag2SO4, which is my compound that needs to break apart, and I'll show you the rest starting now. So Ag2SO4 is going to break down, and it's going to form 2 Ag silver ions, and it's going to form 1 sulfate ion. Now, normally if I did my ice table, these would start off as 0, but because I start in a solution of AgNO3, I know that there's 0.10 moles of Ag already. That's my starting amount of Ag. I actually have that in solution already. The NO3 is insignificant because it's not part of my equation, but the Ag is very significant. So I start with 0.10 molarity of Ag and none of the sulfate. Now, because this is breaking apart, I'm forming this. That means my change here would be 2x, and my change here would be 1x. Remember, the coefficients affect the change the same way. Now, equilibrium. I have 0.10 plus 2x. That's what we would normally write. And here I have 0 plus x, so it's just x. If I go back to previous examples or the work that you've been doing up until this point, you'd know that the x value is going to be very, very small. It's going to be a very small number. So imagine you had $10 and then you were asked to add 2 times a very small quantity like pennies. So you have $10 and you add 2 pennies. That would not significantly change the value of how much money you have. So what you can actually say is you can assume x is insignificant. And if you assume x is insignificant, your equilibrium here actually changes to just 0.10. Molarity is my Ag plus 1 concentration. And so when I work on my Ksp would just be, maybe I'll show that over here. Ksp would be Ag squared and sulfate. Instead of using 0.10 plus 2x, I'd actually just use 0.10 squared and x for sulfate. The reason it's insignificant here, it's because it's like $10.02. Like it's a larger quantity plus a very small quantity, which we're assuming is insignificant. The reason I did not say that here is because, well, 0 compared to 2 cents, well, that's significant. That's on many magnitudes larger, right? So going from 0 to even a small number is significant, but going from a large number to that same large number with a very small amount added to it is not significant. But 0 to even 2 cents, if that's what we're imagining, is really significant. So here I have my Ksp is equal to 0.10 and x, 0.10 squared x. That would mean 0.01 x when we simplify. And knowing the Ksp from the problem, which I have to look up again, it is 1.2 times 10 to the negative 5. 1.2 times 10 to the negative 5. I could just divide by 0.01 and get x is equal to our value of 1.2 times 10 to the negative 3 molarity. That is my solubility of the sulfate, and it's a 1-to-1 ratio, one of these for one of these. So that's also the solubility of this compound of silver sulfate. One of these Ag2SO4s makes one sulfate. So if X is here, that means that's also the solubility of this compound. Cool. I know that's a lot. You're going to be practicing and checking your work using the PDF files I've embedded. I've also included some AP Chem classroom stuff for you to watch. So it is a lot of work. I again expect this to take up to 2 hours. But I'm really grateful for all of you putting your best effort, and for those of you reaching out being like, where's the work? Thank you so much, and best of luck. I'll put a feedback form at the end where you can tell me what you found difficult about today, or what problems you struggled with the most or don't understand. And maybe I can start tomorrow's videos by practicing those problems first. Anyway, I hope you have a great day. Thank you so much. Bye, everyone.